This is Diego with John and Mitchell, and this is our presentation on solar radiation. Solar radiation is important because the sun displays near-ideal blackbody behavior, and through enough research we are able to utilize the energy and radiation that comes from it.
First of all, we need to define what a blackbody is. A blackbody is an object that absorbs all incident light. When the object is in a stable environment, it will begin to produce a radiation known as blackbody radiation. The intensity of the light produced by this electromagnetic radiation depends on the temperature of the blackbody as well as the wavelength of the light produced. The intensity is determined by the equation shown on screen now. As well, the peak of the light's intensity differs depending on the temperature of the object. So we have a visual indication of the temperature of the blackbody. As the blackbody begins to heat up, it will begin to glow red, then move throughout the visible color wavelength spectrum, beginning to glow yellow, white, and eventually blue-white. This is where the term white-hot comes from. So that's a very basic definition of what a blackbody is and what it does.
After undergoing thermonuclear fusion reactions in its interior, the sun releases solar heat energy that travels in space in the form of electromagnetic waves. Solar radiation occurs over a wide range of wavelengths, and using Wien's displacement law, we can calculate its peak wavelength and compare it to that of the Earth. After comparing them, we can see that the peak wavelength of the sun's radiation which is about half of that of the Earth's, which means it has a much greater radiative flux, which is the amount of power radiated through any given area.
What is solar irradiance? Solar irradiance is defined as the amount of light energy from one object that hits a square meter of another object. The photons that carry this energy have different wavelengths that go across the entire spectrum. It's quite important to know the variance of these photons because if photons have too much energy, they could prove fatal to life on Earth. And if there is not enough energy, you could end up with nothing being able to live on Earth. Both ends of the spectrum could end with similar results. Earth's radiance mainly is provided in the visible and infrared spectrums, which is in our favor, as if we strayed to the ultraviolet section, there would be so much energy in the particles, and if we strayed towards the infrared energy of the spectrum, there might not be a lot of energy left. The TSI, total solar irradiance, which encompasses the visible and infrared spectrums, is what reaches the Earth's surface. Ultraviolet gets caught by the ozone layer and some other parts in the stratosphere. However, not all radiation is captured by the outer atmosphere. There is some albedo that reflects the radiation. However, depending on geographical locations and its surface properties, this could vary. Another thing that affects solar irradiance on Earth is due to the solar radiation being affected by the inverse square law, which states that radiation emitted from a sphere decreases with the square of its distance from the center of that sphere. So, energy that comes from the sun gets affected exponentially the further out it goes. It gets exponentially smaller. By the time it reaches Earth, it is not nearly as strong as it was at the surface of the star. Still, that is a lot of energy.
So, the sun's big. The sun's strong. In fact, by using the equation on screen, we find that the sun produces 3.85 times 10 to the 26 watts of power per second. Of those 385 septillion watts, the Earth receives on average 164 watts per square meter of surface, with a maximum of 1,000 watts for locations in direct sunlight. Humans have found a way to harness this power and convert it into electricity through the use of solar panels. By placing two slices of silicon together in like a weird kind of jelly sandwich way, they can form a p-n junction where the photons from the sun's light pass through the n-type slice on the top and into the p-type slice where their energy is passed to electrons. They form a p-n junction where the photons from the sun's light pass through the n-type slice on the top and into the p-type slice where their energy is passed to electrons, which then produce a current of electricity. These solar cells are extremely strong, capable of producing large amounts of electricity. In fact, some say that if only 1% of the Sahara Desert was covered in solar panels, they could produce enough electricity to fuel the entire planet. Of course, the sun produces many different types of energy, and humans harness that energy in different ways. One example is solar thermal energy, which is used to heat water and air in households and businesses. Another way is through the passive use of the sun's heat, such as sunrooms in houses and greenhouses for plants.
In conclusion, realizing that the sun acts almost like an ideal black body, we're able to study solar radiation and how it affects the Earth's surfaces and its atmosphere while using the important inverse square law, as well as remembering Earth's albedo, which is about a third of total solar irradiance. Through continuous research of solar radiation, we can expand the horizons of solar technology and how we integrate it in our lives every day.